Can you see my screen?
Yes, sir. Yes, sir. Yes.
Good.
Clear. Very clear.
Good. So the reference are given. My book with my student, a basic course on real analysis. That will be very close to what I am talking about. Okay. Of course, there are people who swear by Rudin and Apostle, but my preference will be Apostle and Rudin in that order. And whatever I'm going to talk about will be slightly brief. Okay, because of the nature of the talk. But if you want a lot more details from student-friendly versions, you should visit these video lectures of mine. I'll be sending this PDF file to Professor Kala. You can get it from her. So let us get started. So I already had said something about what analysis about, etc. So let me not repeat. Let me start with the next. Okay, sequence xn of real numbers. Let's assume xn converges to 0. Okay. Then I want to say xn is bounded, the sequence is bounded. That is, I want to find a natural number m so that mod xn is less than or equal to m. This should be true for every natural number, right? Now, you can see when I say xn is converging to 0, so if I take an interval around of length 1 around 0, okay, there is a natural number n, so that for every k greater than or equal to n, mod xk lies in this interval. That means mod xk is less than 1. You understand that? That means now you can see I have a collection which depends on the natural numbers. So after a certain stage, everybody is well behaved. I have a very good control, so I don't have to worry about them. That's what I meant. Okay, this is the best part of the crowd. It's very well behaved crowd, so I can simply say I'm going to Lathi charge, they will run away. Okay, then there are unruly fellows, x1 to xn minus 1. Okay, now what do? I want mod xn to be less than or equal to m. So what I do is I find a crude estimate. Look at all these fellows and let's see it to be the maximum of this. This is a finite number, therefore maximum exists. Therefore take m to be either c or 1, whichever is maximum. Then that's going to be satisfy this condition. That will satisfy this condition. Do all of you understand this? Yeah? Okay. So this is a taste of what I said. So in among the natural numbers, that's a huge set. I split into two parts. This is a very huge set, infinite set. This all xk which correspond to this k coming from here, they are all well behaved. Very easy to estimate. And these are the unruly elements. They are finitely many. So this is the trick. What is the trick? The trick is you try to find which are the good elements, what are bad elements. Bad elements you would like to say in some sense small in size. Okay, when I say small, let us call these things as bad elements. The bad elements are small in size. What? I will not write much. I will talk a lot, but I will not write much. What do I mean by in size? Here the number of elements. Here the number of elements is infinite, whereas the bad elements number is finite. Whereas if I take some kind of interval and subintervals here, and bad elements are these subintervals, what do I mean by that? Then I will say the length of these subintervals, add them. These are the bad elements. Let me put some coloring scheme. These are the bad elements. Okay, the bad subintervals. Then what will I say? The bad elements belong to these subintervals. Their total length is less than very small. Okay, this is the trick which you want to do in divide and conquer. Okay, so let us get started with one of the very easy results. And if you understand these 2 or 3, when you read a real analysis book, you keep your eyes open, you will see how many times you use this trick. And you will also feel that you are comfortable with analysis. One of the things which I want to do is the next thing. Let us look at xn. Let us assume again xn converges to 0. I can assume xn convergent, but for simplicity, let me assume xn converges to 0. Then we have what is known as arithmetic average, the average of this. That will be take the first n elements and divide by n. This is the average of x1 to xn. You understand this? Then the claim is an goes to 0. This is what you want to prove. Do all of you understand this? And you can see there is a facility. If you go to participants, can see there is a raise hand, yes or no. When I ask question, if you want to say, you can say yes or you can raise hand. Okay. And I request Professor Sheikh Salim and Somasundaram to mute their mics. Okay, I want to prove this. So what does it mean? I want to estimate mod an. When I want to say this goes to 0. To show an goes to 0, what should I show? You give an epsilon positive, I have to find a natural number n, so that for all k greater than or equal to n, mod an is less than epsilon. Okay? Keep this idea clear, you will see that. But what is an? An is x1 plus xn by n. So I want to say mod an is less than, that is mod of this is less than or equal to epsilon. You follow that? Right. Now, whenever you do analysis, as I said, you should learn to estimate. Do not worry about this inequality first. I want to estimate. What is the obvious estimate for this? Remember, mod of a by b is mod a by mod b. And here b is n, that's a natural number. Therefore, you have an obvious inequality for this. Okay, let me write equality mod x1 plus xn by n. There is an obvious inequality, namely triangle inequality. So I will have mod x1 plus mod xn dot dot by n. Okay. So if I want to say mod an is less than epsilon after certain stage, ak for example. Okay, sorry. I have to say this is less than epsilon. Again, think carefully. Now what do I know? What is the hypothesis? I know xn goes to 0. What does that mean? If you give an epsilon, I know there exists an n, so that for k greater than or equal to n, mod xk is less than epsilon. You follow that? Therefore, if my, let me assume this k here, because I'm using k everywhere, so let me use k here. Okay. If my k is greater than or equal to n, let me write it mod xn plus mod xn plus 1 plus mod xk by the whole thing divided by k. You see that these elements, including this element, they are all well behaved. For which k? For any k greater than or equal to n. Therefore, infinitely many elements are well behaved. You understand this? Only these many elements up to mod xn minus 1, I do not know how to estimate. How many of you understand this? So this is where my divide and conquer comes. So I will say this is less than or equal to, in fact this is equal to anyway, plus mod xn minus 1 by k plus mod xn plus mod xk. Maybe I will write xn so it will be easier. Xk by k. This is actually equality I am writing. Do you understand this? Now, yes? Now, do you see that this is easy to estimate? This is for any k greater than or equal to n. This will be a very large number of elements will be here, but this is very easy to estimate. Why? Each one of them is less than epsilon. But how many elements are there? K minus n elements. Actually, n minus 1 or whatever. It is k minus n elements. Okay? Each one of them is less than epsilon, but then I am going to divide by k. Therefore, this is, I have an estimate for this. And remember, this is very large. K could be as large as you want. Therefore, there are infinitely many elements. Still, I can make sure this is. So now you can see the bad elements are only finitely many. Right? Therefore, what do I have to do? See, this k minus n by k is less than 1. Therefore, this is less than epsilon. So I want to make sure this is less than epsilon. I am through. How do I make this less than epsilon? Now remember, I already said xn converges to 0. That means there exists an m, so that for all n, mod xn is less than or equal to m. Right? You follow that? This is for all n. Yeah? Therefore, each one of mod x1 up to mod xm, that will be less than or equal to m. So how many elements are there? There are, look at that, there are capital N elements here. There are capital elements. Each one of them is less than capital M. Therefore, there are capital M n. That is an obvious estimate by k plus something epsilon. Notice that you gave me an epsilon. This n is fixed. This k is also fixed. So what all I have to do is I have to choose a k large enough. So we choose a k naught so that mn by k naught is less than epsilon. This is possible by Archimedean property. You see that for this epsilon, once you get this m is already given. The moment xn converges to 0, this is given. and once you give an epsilon, this n is obtained. Therefore, that's also fixed. Therefore, this finite number of elements, I use a crude estimate. These are like third degree method. Okay, these are all ruffians. Use third degree method, put a brutal estimate. So I got that. Okay. Now, luckily there is a k, but it could be as large as I want. So what I do, I choose a k naught so that n by k naught is less than epsilon. Okay. Therefore, if k is greater than or equal to k naught, this first finite sum is less than epsilon. And when my this k is greater than capital N, this tails sum that is less than epsilon. So what do I want? I want both to happen simultaneously. So you choose a maximum. So you have proved it. How many of you understand? I'm not writing a textbook proof. I'm not writing. Okay, I want you to think along with me. It may be a little disconcerting, but you should get used to that. How many of you follow that? Can you say, raise hand if you follow that? You may have to go and read a book if you want, okay? Because this is not the way you are usually taught, then you'll have difficulty. Okay? Because I want to think. I don't want to kind of keep from memory and write the proof. Okay? Textbook proof I never write. Okay. It's a somewhat disappointing response. Okay, good. So let's go back to the proof. Do you see the divide and conquer rule? I wanted to prove mod an, okay, goes to 0. That means I have to show that for n sufficiently large, mod n will be less than epsilon. Okay, that means I have to estimate this. To estimate, when I write, I have an obvious estimate, then I break it into true sums. So this is the sum which is well behaved. And remember, k can grow to infinity. Therefore, there is a large number of terms. They are all well behaved. So I have an easy way of estimating. But here, I don't know any fine estimate. So I have to use a very, very crude estimate. Namely, each one of mod xn, x1, x2, x capital N will be less than or equal to some constant, namely m. How many such elements are there? N. They are finitely many. This is what I said. What is that? Bad elements are small in size. Therefore, I have to have a control. Okay. Learning analysis, thinking mathematics like this will help you to enjoy. Okay. Otherwise, you will only think mathematics is a verification. It's not a creation. It's not a discovery. Okay. That's the first thing. Okay. Now let's look at the second thing. I'll also give a second thing which are somewhat easy so that you will get used to that. Okay. All of you know about integrability, right? Riemann integrable. Okay. There is what is called a, so I have a function here from bounded function from AB to R. Okay. I want to say f is Riemann integral on the interval AB. Okay. Then you have the, for any partition P of AB, okay, this is my partition xi minus 1 xi. Okay. Then you have what are called mi of f. That is a LUB of the function fx, where x varies over the interval x minus 1 to xi minus 1 to xi, this one. And similarly, small mi, which is a GLB. If you are fond of Latin, it's a supremum and infimum. Okay. So what does Riemann's criterion for integrability say? It says in terms of upper Darboux upper sum and lower sum. What does it say? It says that given any partition, you define, okay, upper sum of the partition of F with respect to the partition P is summation capital Mi into the length of the interval xi minus 1. I am not writing F because F is fixed now. And similarly, lower sum is small mi of the length of the interval. Okay, I don't want to get into the geometry of this. You must have been taught by your teacher. This is one. And Riemann's criterion says F is Riemann integrable on the interval AB if and only for every epsilon positive there is a partition P of AB so that UFP minus LFP UFP is always greater than or equal to LFP, you want to say it's less than epsilon. This is the so-called Riemann's criterion. I hope most of you have seen it. I'm going to use it. Right? Now let's try to understand. Here also you will see there is something like divide and conquer rule comes. I want UFP minus LFP is less than epsilon, right? If I want to prove F is Riemann integrable, if you are going to give me an epsilon, then I have to find a partition P. That I do not know. Okay, that I will do later. With what property? The upper sum minus the lower sum should be less than epsilon. I have the expression for upper sum and lower sum. So what is that? That is equal to capital Mi minus small mi into xi minus xi minus 1, I equal to 1 or whatever it is. That is this object. I want this to be less than epsilon. Yeah, look at this. See, you should not jump into the probe. Okay, you should know what you want to do. Look at the goal, try to see how to reach the goal. You have to devise a plan, right? When you have some kind of a thing, your goal in your life, what do? You plan it ahead. Okay, what are the steps I have to do to achieve my goal? So you don't simply jump into that. So similarly, mathematics also same. My goal is I have to make sure this is less than epsilon. What do you think I can make sure? You can look at this capital Mi minus small mi. That is what? This is essentially the max oscillation of the function. That is, this is the, so think of this as supremum as a maximum, LEB as a maximum of the function in the interval, just for intuitive reasons. And similarly, GLB, think of the minimum of the function. So what do I want? If this fellow is less than epsilon, then I am happy. You understand that? If I can choose a partition P such that in each of the partition, my capital Mi minus small mi is less than epsilon, then what do I have? This will be less than epsilon times summation xi minus 1. But that is equal to epsilon to b minus a, length of the total interval. It's as good as epsilon. Otherwise, I would have chosen this capital Mi minus small mi will be less than b minus a. Okay. Do you understand this? Right. So now I break this sum into two parts now. Okay. First, think about when can I make sure capital Mi minus small mi is less than epsilon? Some kind of continuity. Right. If F is continuous and hence it's uniformly continuous on the interval AB, I can choose a partition such that the oscillation, that is a maximum and minimum are attained in each of the subintervals which are closed and bounded. Therefore, I can make sure it will be less than epsilon, any pre-assigned epsilon. So I would expect it will be easier for me to control this if the function is continuous on this interval. Okay. So when I want to prove a function is integrable, then what do is I split this sum, this set. This is already a finite set. Okay. I am going to split it into two parts, G union B. What is G? G consists of all those I which such that capital Mi minus small mi is less than epsilon. What is B? Now all of you know it must be. They are the bad elements. I do not know. You understand that? Therefore, my UFP minus LFP, I can break it into two sums, I over G plus I over B. Notice that both are finite sums. So what do I mean by saying the size is small? Go back. Bad elements are in size small. Look at this picture. I had this in mind. That's why I drew this picture. So what should I do? So in the good thing, capital Mi minus small mi will be less than epsilon. Therefore, it will be less than epsilon times xi minus 1, I running over G. But notice that the sum of the subintervals contained in AB. Therefore, this will again be less than or equal to B minus A. Therefore, the first sum will be less than or equal to epsilon times B minus A. But let's look at the second sum. This is going to be capital Mi minus small mi into xi minus 1. Now here it is not less than epsilon. Okay, it's actually greater than or equal to epsilon. So what kind of smallness should I expect? My picture already showed you. Notice that my function f is bounded. Therefore, mi minus mi will be less than or equal to 2 times c if suppose this is bounded by a constant c. Therefore, this will be less than epsilon to b minus a is the first sum 2c times summation xi minus xi minus 1. Now, can somebody tell me what I should make small? I have to say the sum of the bad intervals, the length of the bad intervals should be arbitrarily small. You see that this is the trick. If you go through your Riemann integration proof, most often this is what you will be using. I am looking at the simplest example. There are complicated examples, but I want you to understand the tricks. Once you learn the trick, you can go to any book, especially my book, you can learn that. Let us look at a very concrete example. Suppose I have minus 1, 1, this is the interval, and this is 0. Let us look at this. So on this interval, my function is 1. Okay. And on this interval, my function is 2. At 0, I have to define, at 0, the function is 10 or even, okay, 20. It's a 2021, but it's okay. You understand the function? Okay, how do I write the function? Fx is 1, if 0 less than, sorry, minus 1 less than or equal to x less than 0 equal to 2020 if x equal to 0 and equal to 2 if 0 less than x less than or equal to 1. That's it. Yeah. Now I want to know whether the function is integrable. Look at the graph. Graph will be something like this. 1 up to this open, and here again open at from 2, and here it will be something huge. It goes above this, right? Now you should be able to see, I can assign an area. This area will be 1, this area will be 2, therefore the total area should be 3. So the function should be integrable. How do I prove that? Okay, now let's look at what kind of partition should I choose. I have to choose a partition where capital Mi minus small mi I can control easily. Now do you see that? And where the problem comes, capital Mi, see, if I choose any interval around 0, okay, and here there are points where the value is 1, here there are points where the value is 2, and here there is a point 0 which is 20, right? Therefore, in any interval around this 0, my capital M will be, that is the maximum, will be 20. If you don't like, make it very small so that you can cope with it. And what will be say? Minimum will be 1. Are you following? Therefore, my capital M minus small m for any interval around 0 will be less than or equal to 20. Actually, 20 minus 1, but that doesn't matter. Right? So I can think of this partition minus 1, 1, keep a 0 and put, see, the bad points belong to the interval. What do I want? The total sum of the lengths of such bad intervals should be small. So what do I do? Around 0, I choose something like 1 by n very large, or n very large, minus 1 by n to plus 1 by n. Okay. So what is my partition? Partition consists of 3 subintervals. From here to here 1, and from here to here 1, and from here to here the third. And for this interval, my m, capital M and small m both are 1. Therefore, the contribution from here will be 0. Are you following? Okay. This is the first interval. This is my x0. This is my x1. This is my x2. This is my x3. Okay. Therefore, the first one will be capital M1 minus small m1 into x1 minus x0. That I know how to write it, but let's not worry about. This is 0. The next one will be this minus this. That will be 2n, the length of the interval. And this will be less than or equal to, it's not exactly, otherwise I should write 2019. And here also the capital M equal to small m equal to 2. Therefore, that is also 0. Into this is x3 minus x2. Okay, 2 by n is the length of the interval. That is x2 minus x1. So what do I want? I want this to be less than epsilon. Do you follow that? How do I do that? This is something like 4040, okay? By n, I want to be less than epsilon. By Archimedean property, I can always choose a natural number n so that this can be made less than epsilon. Do you follow this?
Sir, maybe people have to unmute and respond. Maybe.
No, please. They don't have to. That's why I said they can use the symbol, okay, raise hand, or yes, they can say that. See, click on your participants, you can see raise hand is there. So when I ask yes, you can say yes or raise hand, but I prefer raise hand because yes has only for 10 minutes of life. So before 10 people would have raised hand, before 11th comes, the 10 would have vanished. So I will not know how many had raised hand. Said yes, okay. Anyway, the response is not that good, only 3 people. Yeah, it's a really tough, right? Because mathematics means I should write on a board, you should copy.
Sir, actually, for students, this Zoom meeting is new to them, so that is the reason they can't find where to chart and where to.
No, that response wise yes, but let them. Okay, I would like to hear. Let them unmute and say yes. Let us see. Out of 30 odd people, at least 20 say yes. Yes, can you unmute and say? Because in the classroom, they are not engaged, interactively. They are always little diffident. Lecture is only to attend and take notes, right? Okay. Right. So there is a third thing which I would like to do. Because this is a very easy one. The third one will be a little difficult. So I'm a little hesitant. All of you know infinite series, right? I will not write 1 to infinity, etc. Okay. I will write only an. Okay. And there is another infinite series bn. Let us assume both are convergent. Okay. Then there is what is known as a Cauchy product of the 2 infinite series. That is given by mimicking polynomial definition. Suppose I have a0 plus a1x plus am x power m and b0 plus b1x plus bn x power n. How do I multiply? I multiply and then collect the coefficients of powers of x, right? If you do that, you have this formula. We will assume 0 to infinity here. Okay, I said I will not write, but anyway, let me write for the time being. Okay, a0 is also defined so that life will be easier for me. So my C0 is A0, B0. C1 is, let us say, when I multiply, what will I have? This is the power of x. The A0 into B1 into B0 into A1, that will be x. Therefore, I have A0 B1 plus A1 B0. So what is C2? A0 into B2. This will be x squared, right? And A1 into B1, that will be x squared. Then next will be A2 x squared into B0. So you can see the pattern. So the sum of these 3 things to add up to this. So it is going to be A0 B2 plus A1 B1 plus A2 B0. So in general, you can write down Cn. Cn is going to be A0 Bn, A1 Bn minus 1 plus An B0, which is, let us write it as AR plus Bs, where R plus is equal to M. Okay, of course, 0 R. Okay. Do all of you understand? This is what is called Cauchy product. This is got out of this. So the natural question one asks, why it is natural is another thing. You can also ask, why can't I take A and Bn as a new C thing? Okay, that's not the way. So you get a new series which is called n equal to 0 to infinity. This is called the Cauchy product of the 2 series. The question is, if I assume this is convergent and this is convergent, can I conclude this is convergent? Okay, these are convergent. Does that imply the Cauchy product is convergent? Okay. This proof is a fantastic example of divide and conquer rule. Okay, it's the same trick. Okay, please bear with me. You and do not worry about and trying to understand 100%. Okay, that's a kind of myth. Okay, 100% you it's a kind of an ideal. You keep on reaching it like a infinity. All right. So it's a myth because many teachers have the delusion that I taught so well, my students should have understood 100%. The understanding is the students, not the teachers. So students have to struggle to understand. Okay, I can only give you the path how to go to that. Okay, so how do I do that? So let us look at. So I have to prove summation Cn is convergent. Let us look at, let us recall the definition. What is this? When do you say this series is convergent? Okay, let me use as easier notation. I will write An as the partial sums of this series Akk equal to 0 to n, and Bn partial sums of the series Bk k equal to 0 to n, and capital Cn. This will be confusing, which is small c or capital C, but let us assume that Ck is 0 to n. Okay, so to show this is convergent, what should I show is that Cn should converge. Okay, this converges to what? Can somebody guess? And those of you who think this is little abstract, it's not abstract, because let us look at, suppose I have A1 plus A2 plus A3 and B1 plus B2 plus B3. Okay, or let's say B2. Okay, this sum is A, this sum is B. Then what kind of product will give me this product AB? You have to use distributive law, right? You understand? A1 B1, A1 B2, A2 B1, A2 B2 plus A3 B1, A3 B. Then only I will get equal to A times B. Do you understand? Okay. Thing, mathematics is common sense. Okay. It is not some kind of weird or anything. So I want to prove this converges to AB. Yeah. So how do I prove that? Again, it's a very interesting thing. Let us look at Cn. I have the formula. So let us look at Cn. I will only slowly I will indicate capital Cn. No, first let us see Cn. Cn is A naught B. So Cn, right? A naught Bn, A1 Bn minus 1 plus An B naught, and C naught Cn. C naught will be A naught B naught. C1 will be A naught B1 plus A1 B naught, and so on. So capital Cn will be C naught plus C1 plus Cn. These are small. I'm sorry, maybe I will use gamma for the partial sums. So that, okay, I have to add this. Now you see that. Now look at this. Add vertically, A naught times B naught comes here. In C1, A naught times B1, and Cn I get A naught times Bn. Do you follow that? Next will be, I will start with A1 B naught. A1 B naught will start with A1 B naught, A1 Bn minus 1, and so on. Okay. Are you following? I hope. So A naught will be, I have to add B naught plus B1 plus Bn. And then next N will be B naught plus Bn minus 1. Because remember, I should get N when I add up these two things. Last one. And the last one will be A naught Bn. So A and B naught. Are you following? And what is this? This is A naught, but this is the partial sum Bn. And this is A1, this is the partial sum Bn minus 1. And this is An. I will call it B naught, but it is same as B naught. Okay, this will be An minus 1, B1. So am I clear? Yeah. Now what do? I want to show gamma n converges to AB. You understand? Keep always the goal. See, in textbooks, they keep on writing. Okay. Finally, the goal drops out. Okay. So you don't, most often you think that you are checking the proof line by line. You are verifying. You are certifying the author is logically correct. But you may not have an idea how the author got that proof or how you can get the proof. Now I want AB, right? Gamma n should converge to AB. Therefore, I want to manipulate so that the AB comes here somewhat. Now let us look at Bn. Okay, if n is large, Bn is going to be close to B. Therefore, I can write this as A naught into, okay, B minus Bn. Okay, sorry. Let me write Bn minus B. That means I subtracted, therefore I have to add it. A naught B. This is add and subtract trick. And here what will I do? The same thing. I will write A1, Bn minus 1 and B. Therefore I will add A1, B. I subtracted. Are you following this? Yes? Yeah. So what will I get finally? I will get A and B. The last one will be A and B 0. So I will get A and B. Okay. Last one will be A and B0 minus B. Therefore that has to be added. And now look at it. See, this is how you learn analysis, not by writing proofs carefully and copying down. I'm writing so that it looks little legible possibly. I do not know. Now look at this object. What do you think you will do? What will be your natural intuition? You see B is common. Therefore I can write this as A naught plus A1 plus AN times B. Do you understand this? I am writing the same thing. But what is A naught to AN? That is capital AN. Okay. So I have said gamma n equal to this object plus A and B. So as n tends to infinity, I want to say gamma n tends to AB. Look at this equality. There is something which is striking. Remember, what is AN? AN is the partial sums of A. Therefore, where does it converge to? It converges to the sum of the series summation AN. That means A. Therefore, this fellow, as n goes to infinity, it already converges to AB. Do you understand this? So there is some kind of light at the end of the tunnel. So I have got gamma n converging to AB seems to come through, but then there's a problem. I have to look at this. What do you think I have to do? Again, notice that if n is very large, Bn minus B is close to 0. Do you follow that? Yeah. So if n is very large, I can make all of this close to 0, but then I am in trouble. I am going to get something like An minus 1, B1 minus B. Okay. So this kind of thing will be problem because B1 minus B, it's like what I did earlier, right? If xn converges to 0, after certain stage, all xn will be very close to, okay, less than epsilon. But the first few terms I have no control. So similarly here, B1 minus B, B2 minus B, B0 minus B, I may not have any control. Do you understand? Think mathematics, you will see the fun, you will enjoy. It's like having a control, right? People like to have control over others. So you would like to have control over this also. So that is what divide and conquer says. So this term, the last term goes to AB, therefore it's fine. Now here if I look at if n is very large, these terms may go to 0, but then these may not. But what do I know about summation AN? That is convergent. If summation AN is convergent, what do I know about limit AN? The sequence AN converges to 0. Therefore, if n is where, okay, this may not converge to anything, but then this AN will be very close to 0. So there is a kind of balance. You understand that? Either these terms seem to be going to 0 or these terms going to be 0. So I have something like AR into B n minus R minus B. So if n is very large, okay, then this may be close to 0. Suppose my n is greater than or equal to 2n, okay, therefore Bn, okay, minus B is less than epsilon. Therefore I can make this less than epsilon. If my R is also less than or equal to capital N and little n is greater than or equal to 2n, then this will be greater than or equal to capital N. Therefore this minus this will be very less, okay, and therefore I can control this. But if this is the case, if R is very large, then n minus R will be very close to 0, B0, B1, B2, etc. Therefore I may not be able to control. But then I know if R is very large, then this will be, I will be able to control. Do you see that? We are dividing and trying to conquer. I will give you 20-30 seconds. Please enjoy. Do not worry about whether you will be able to write a proof. Nobody is going to ask this. Okay? Mathematics for understanding, not for exam purpose. No. Okay? So how do I achieve that? Okay, I am going to give indication how to do that. So what are the things I know? I know Bn converges to B, okay, and An converges to 0. Somehow I want to make use of that. Therefore this means Bn minus B goes to 0. This is actually if and only if. Okay, right. So I want to make use of those two things. So how will I see? This one is no problem. This always goes to A and B. As n goes to infinity, this will go to AB. Therefore what I have to show is this object, okay, this goes to 0 is what I have to prove as n tends to infinity. This is not your classroom text. I am not writing. I want you to think along with me, at least partially. Okay, so how do I arrange it? First notice that if even though An goes to 0, remember this, what kind of objects I have? I will have some objects like this. B n minus R minus B. Okay, if R is very, very large, this will be very close to 0. But as n goes to infinity, I have to see the behavior of this. Because if I have xn goes to 0, I cannot say something like yn times xn also goes to 0. Unless I know yns are bounded. Do you understand? If you begin to think mathematics, this is fun. So that tells me that I have to prove this is bounded. That is obvious because Bn minus B goes to 0. Therefore, I know it is bounded. Therefore, this fellow in modulus will be less than or equal to C times mod AR. Okay, it's independent of N and R here. This will be less than or equal to C. This goes to 0. Yeah. Now, how do you estimate these things? The first terms, where I have something like A naught into Bn minus B, etc. Let me assume my n is greater than or equal to 2n. What is this n? This n is my Bn Bk minus B modulus is less than epsilon for every k greater than or equal to n. You understand that? Therefore, if I take my n to be greater than or equal to 2k, up to capital N I can go. Okay. I am breaking this sum into two parts where Bn minus B's are small or where mod Ans are small. You understand that? That is my divide and conquer. Okay. So I want this to be less than epsilon. Right? Now can I do that? Therefore, if I look at the estimate, you will see something very interesting. What is the obvious estimate I have? This is a triangle inequality. Right? And since my n is greater than 2n, and here I am going only up to n, each one of them will be less than epsilon. Therefore, I will have epsilon times mod a1 plus mod a1. So once you are given me epsilon, okay, this number is finite times epsilon. Therefore, up to capital N terms I have mastered. I can make sure it's a constant times some epsilon. So I have to make sure the rest of the things are less than epsilon. Now remember here n is going to vary. That is going to create a problem for me. Okay. Please try to understand, follow at least 20-30% and read a book, you will understand. So now I am looking at after my n, okay, capital N term, I am looking at terms. Therefore, my R is greater than or equal to capital N, or n plus 1 if you want. So I have AR into B, n minus R minus B. This is the kind of terms I have. Okay. Where R is greater than or equal to n up to going to n, where my n is greater than or equal to 2n. I want to estimate. So what did I say? The only, remember this n is greater than or equal to 2n, and n is allowed to go to infinity. Therefore, infinite there in some sense it's a large number of n's are going to be there, large number of terms. So I have to have a control. Okay. So how do I do that? I already know this is less than or equal to c. Therefore, the obvious estimate for this will be c times summation mod AR, okay, R greater than or equal to n up to n, where c is the bound which we wrote for this, or epsilon I wrote, but it doesn't matter. No. Where did I write? I wrote something. Yeah, here. Yeah, that is the c. But now do you see something? I want this to be less than epsilon. Notice that this c is also fixed because you said bn converges to b. Therefore, bn minus b goes to 0. Bn minus b goes to 0. Therefore, mod bn minus b is always bounded by c for all n. Okay. Therefore, this c is fixed. It is not depending upon your epsilon, etc. So this is all right. But I have this. But this n is allowed to go to infinity. So I want this sum should be some less than epsilon. Now you see that in the theorem, your teacher will assume mod an is absolutely convergent and mod bn is convergent, then the Cauchy product Cn is convergent. Okay. Now we see that we are forced to assume that because I want to say this is less than epsilon. How can I say that this will be less than the n to infinity of mod AR? Right? The tail of the series must be less than epsilon. What does that mean? The series must be absolutely convergent. So I have to put extra assumption, then I get this. Okay. One can write a textbook proof. You will see in my book or Rudin. But people who read from Rudin, when they come to lecture, they get confused because this kind of analysis they are not done. Line by line checking will not make you confident. It will make you confident it's logically correct. Okay. So this is the fourth application. The next application I want to talk about is something to do with integral. All of you might have studied a so-called improper integral gamma function 0 to infinity e power minus t and t power x minus 1 dt. So I want to say this improper integral exists. Yeah. Now how do you do that? Again, it's a divide and conquer. Notice that the whole thing is a continuous function. The integrand e power minus t to t power x minus 1 is a continuous function. No problem. Therefore, at any finite interval, that is any finite interval, this integral will exist. A to b of this will always exist. Okay. Therefore, the problem is the domain is infinite integral. towards infinity. Towards infinity, you can again see the behavior of the function looks very nice. X is fixed, therefore t power x minus 1, even when assuming x is greater than 1, okay, right? This will be all right. Okay, if x is greater than 1, as t, okay, as t goes to infinity, this will go to infinity. But then remember, e power minus c intuitively will go to 0. Therefore, as t goes to infinity, this x is fixed. You understand? X is fixed. If x is greater than 1, let us say, for example, x equal to 2, then this will be something like t. As t goes to infinity, this will be infinity. But e power minus infinity, we know it goes to 0 much faster than any polynomial. So our intuition should be towards infinity, this should be very, very small. But that's not enough, because let us look at 1 by x. Okay, this function is not integral to 1 to infinity, right? Even though this function goes to 0 as x goes to infinity. You follow that? So I need a better estimate. I know it, this exists, but not x power p. In fact, all of you must know 1 by x power p dx exists if p is greater than 1. Anyway, so I want to do this. How do I do that? So I want to say somehow e power minus t kills this going to infinity. See, if x is greater than 1, t power x minus 1 goes to infinity, but e power minus t goes to 0. But the product I want to say is well behaved. If okay, that is integrable. That's all I have to say. How do I do that? Okay. So what I am doing is really hard analysis, so that you will appreciate how to think. Whereas in textbook they will only write line by line proof. You should learn how to do that. So I want to make use of this. So let's look at e power t. What is e power t? E power t is t power n by n factorial 0 to infinity. And notice that we will assume t is positive for the time being. Therefore, e power t is always greater than t power n by n factorial. Again, it involves the definition of sum of an infinite series, because this sum is supreme over the partial sums. Okay, therefore any partial sum Sn is greater than or equal to Tn by n factorial, and this is the sum is supreme of Sn, that is the sum. Therefore supremum will be strictly greater than this. This is actually strict. Anyway, you understand that? So this is what we want to do. In particular, t by 2 again it will be 2 power n. Okay, you follow that? E power t by 2 will be t by 2 to the power n by n factorial. Therefore, e power t by 2 is greater than t power n by 2 power n into n factorial. Yeah. Now what do you do? Let's look at. I want to say e power minus t into t power x minus 1. Okay. I want an integral function. So let us look at this kind of function. Do you think it will be integrable? Some e power minus t by 2 dt. This is a primitive. You know how to integrate. This is a very elementary thing. Therefore, you know this is finite. So what I want to say is this is less than or equal to e power some t by 2 by some constant. Okay. Therefore, this will be integrable by comparison test. Okay. And you just have to do this. I will get it. So the point I am trying to say is divide and conquer is very, very important tool in analysis. Look at the behavior of the function, what you want to do, and decide. For example, let's look at the first thing, xn going to 0. I saw for n sufficiently large, I know how to control. Therefore, only finitely left out. Now let's look at this step function kind of thing. I know I have to choose a partition so that upper sum minus lower sum is less than epsilon. Then what do? I looked at it. Capital Mi minus small mi. Whenever these bad points are included, I have no control over that. So I have to control the length of such intervals. So I controlled it by putting the bad point in a very, very small interval. Okay. And third thing here, what did I do? I again break the sum into two parts. Okay. And luckily this part behaves well. Then this is the part I have, okay. As n goes to infinity, there is a huge thing that I break into again two parts. there is a finite part which comes up to capital N, and after that this is the infinite part. Okay, this is the kind of trick which is needed. And coming to integration, again the same integral, I have to break it. When you go to measure theory also, you will see the same trick. Okay. Okay. So there is one more thing. I will only state it, but I think all of you may be tired. Suppose I have a function f from AB, okay, to R, let us say small m to capital M. Okay, that is a minimum, or that is the GLB and LUB of the function f on AB. Okay, and this is a function G to R. Suppose this is continuous, and suppose this function f is integrable on AB, then I have a composite function G composite f from AB to R. Okay, I want to say this is integrable. Okay, so I'll just indicate what is the idea behind that. So what is that I have to do? I have to find a partition so that u of G composite f P minus L of G composite f P is less than epsilon. I have to find a partition with this. But what is this object? This object is capital Mi of G composite f minus small mi of G composite f. Okay, times xi minus 1. Now notice that G is continuous. Therefore, my small, this mi of f and capital Mi of f, if they are sufficiently small, capital Mi of f, where do they live? They live in the interval small m to capital M. Okay, suppose this interval length is sufficiently small, since G is continuous, therefore I can make sure this is less than epsilon using uniform continuity of G on this interval, right? But then if Mi of f and capital Mi of f, they are far apart, then this is large, then I cannot be controlled. Therefore, I have to make sure this sum of these intervals is less than epsilon. You see that? It's exactly what I did earlier. So I break this part like this. Find a partition I so that capital Mi of f minus small mi of f is less than epsilon, and the bad will be this is greater than or equal to epsilon, right? And remember, G is a continuous function, therefore it's bounded, therefore this again will be less than or equal to 2 times C. Okay, therefore the sum over I in B of capital Mi of G composite f minus small mi of G composite f, okay, into xi minus 1, this will be less than or equal to I over B into 2C times xi minus 1. Okay, so somehow I have to make sure the sum of the bad subintervals is very small as I please. Okay, how do I achieve that? This is where I use f is integrable. Since f is integrable, there is a partition P so that u of P minus L of P is less than epsilon. You understand this? Therefore, let me write the same thing. I in B, therefore u of P minus L of P will be greater than or equal to this. Okay, epsilon is already greater than this. I am reversing this direction, and this will be only finite sum. Therefore, u of P minus capital Mi of f minus small mi of f, yeah, into xi minus 1. Therefore, epsilon will be greater than or equal to summation this. This is, if you want to call it some eta. We will fix the eta later. So eta is greater than or equal to this fellow, and this is greater than or equal to epsilon. Do you understand that? Yeah. Therefore, epsilon into xi minus I running over B. But this epsilon comes out. This will be B minus A. Therefore, I can make sure the sum will be less than that. So let me just quickly go through that. The last thing. So I choose some given any eta, I choose a partition so that U of P minus L of P is less than eta. Right? Now, therefore, in particular, let us look at I over B, capital Mi of F minus small mi of F into Xi minus Xi minus 1. This will be greater than or equal to summation over I epsilon into Xi minus Xi minus 1. This is the sum of the bad intervals, length of this bad interval. You see that? That's greater than or equal to epsilon. Therefore, the sum of the length of the bad intervals Xi minus Xi minus 1 is less than or equal to eta by epsilon. Yeah. So usually books will choose eta equal to epsilon squared. Okay, given epsilon, choose eta equal to epsilon squared so that U of P minus L of P is less than eta. Therefore, I will get the sum of the bad intervals will be less than eta by epsilon, which is epsilon squared by epsilon, which is epsilon. Therefore, this sum, whatever we wrote, the bad sum, okay, that will be less than. Therefore, the bad sum I over B of Mi of G composite F minus small mi of G composite F into Xi minus 1. This is less than or equal to 2C times, okay, epsilon, because that is sum of Xi minus 1 I in B. Okay, that we said it is less than epsilon. Therefore, we proved the sum over the bad part is also less than some constant times epsilon. The first part is already less than epsilon times B minus A. Therefore, the function is Riemann integrable. This is the standard proof you can see in any of the books. But my point of this was only to express okay, let me see. Are you able to see me now?
Yes, sir. Yeah, yes, sir.
Okay.
Yeah.
Right. So the point of my exercise was to kind of give some kind of an idea about why the divide and conquer trick pervades the entire analysis. Okay. And you may go through some real analysis and analysis on Rn, measure theory, and complex analysis and functional analysis, all those things. But this point is not brought out because people are always kind of very shy of saying what is the intuition behind certain proofs, why certain proofs work. Okay, that's how I'm on. It's like cultural difference. Okay, about 100 years ago in Tamilnadu, people can wear dhoti, and if at all there may be some mangavastram on their chest, otherwise nothing, they will walk. Now men folk don't want to walk like that, right? They want to walk with a banian and shirt. Yeah? Because you think that you are uncultured. The same way, mathematics also have developed that kind of thing. Okay, when I say something, okay, the intuition should not play a role. I have to prove rigorously. But then you forget. See, creation always is somewhat vague. You have to understand. Then once you understand properly, you want to disseminate the knowledge, explain the knowledge to others. At that point of time, what you do is you codify it so that it will be acceptable to all. This is how mathematics is developed. Unfortunately, mathematics is not practiced that way. I tried to change, but then it's an uphill task, as you might have just now found out. Okay, thank you very much. I'm open for questions.
So, any questions?
Okay, if there are no questions, I will ask questions.
Yeah.
Will any of you, at least one or two proofs you would like to go back and read?